Hi, everybody. We're here in section 5.3, which is titled The Fundamental Theorem of Calculus, which means this is going to be important, right? So I'm excited to be here. We're going to look through, the notes here. You're even going to watch a video here, if we've got time, from 3 Blue 1 Brown. It's actually a continuation of a video that, we had watched a couple classes ago. But first, I think before getting into the definitions and the examples and all that kind of stuff, we're going to do something that feels a little bit more like an activity in a way, because, I did originally write this up as an activity of sorts. And so there are, questions here. There's enough information that you guys probably could do this on your own if you wanted to. If you want to take the time to work through this, on your own in small groups and that kind of stuff, like an activity, that would not be a bad use of your time. But if you spend too much time working on this, you probably won't have time for the, the other video. You guys do whatever makes sense to you. But what I'm going to do right now is work through this myself, so you can, pause and work along the way. But yeah, I'm going to do this activity because I think developing area functions kind of from the ground up is going to make more sense. It's going to help the fundamental theorem of calculus actually be a little bit more concrete. Okay, so we're here. We're going to draw the line y equals 2t plus 1 and use geometry to find the area under this line above the t-axis and between the vertical lines t equals 1, t equals 3. And we can use the formula for the area of the trapezoid. Okay. It's lovely when my app just decides to quit out. Be right with you. Come on. All right. Don't think. That's fine. All right. So we need the line y equals 2t. Plus 1. So that means we got a y-intercept of 1. That means we're going to have a slope of 2. So that means our next point's going to be at 1, 3. Our next point's going to be at 2, 5. Our next point's going to be at 3, 7. And so, all right, there's our line. Now, we're just going from t equals 1 to t equals 3. And yeah, if we're going to find the area of this trapezoid, all that, what do we do? 1/2, we're taking the average of the two bases, which in this case, the bases are the parallel things. So this is 3 units long. This is 7 units long. And then we're multiplying times the height, which I know it doesn't look like the height here, but yeah, the height is 2 units long. We got to orient ourselves to the trapezoid rather than the axes on this formula. But anyways, that's half of 10. 5 times 2 is 10, right? Oh, okay. So the area of this trapezoid is 10 units. Cool. So that's just, getting familiar with calculating this. Now we're going to get into the area function part of it, where we're going to start off at 1, like we did here, but our next boundary is going to be located at t equals x, and we're going to have this next boundary be movable. Imagine that this thing is a slider where x can, move either way, but we still have our line 2t plus 1, and line looks something like that. So we're still going to be getting a trapezoid shape, but the right-hand side of the trapezoid is allowed to move. The idea is we want to create a function that when we input some x value here, we get the area out as the output of that function. So we sketch this region. So let's go ahead and use that trapezoid formula again. Area equals 1/2 sum of the bases times the height, 1/2. The first base is going to be 3 again, because this is just, I don't know, y, or yeah, our function here is y equals 2t plus 1. We could call it f of t as well, and that's probably what we're more used to. Let's call it f of t. And then down here, this is, f of 1, which is equal to 3 for the height. And then this height is going to be equal to f of x, which is going to be 2x plus 1, right? And then this distance down here will be x minus 1 for that height. Okay, so let's keep going. The other base here is 2x plus 1. And then the height was x minus 1. All right, so let's see what we can do. We've got 1/2 times 2x plus 4, and then times x minus 1. All right, so let's multiply that 1/2 in. Then we just have x plus 2 times x minus 1. Ooh, and we get x squared minus x plus 2x minus 2, and x squared plus x minus 2 as, okay, a function, area as a function of this slidable second boundary. Cool. Yeah, that looks like an area function to me, and it looks like we've got it, pretty simplified, so I think we're in a good place. Explain why a of 1 equals 0 should be true. Well, if we make x equal to 1, that means that we'd have no area. We'd just be looking at the little skinny strip there. No width to the trapezoid. And indeed, if we put in 1 for x here, we'd get 1 plus 1, which is 2, minus 2 equals 0. So, we can check that off the list, that a of 1 is equal to 0. And one of the things that we might want to check real quick is, is a of 3 equal to 10 that we found before? And if we put in 3 here, we'd get 9 plus 3, which is 12, minus 2. Things are looking promising. It looks like we've got a good area function here. With this, slidable right boundary. Okay, now that we have a function a of x, we're ready to consider how a of x changes with respect to x. Draw another vertical line on the graph directly above at t equals x plus delta x, where delta x is some small positive number. Okay, so I'm actually going to, no, all right. I'm going to move this out of the way so that we have a little bit more room to write so that you guys can see it. But the idea is we're going to create a little delta x, worth of distance here. And I don't know, follow that up so that, that should be a straight line, and it's not even close. I got bumped. Yikes. Okay, another vertical line. Cool. So now we've got a shape. So this is X, and then the right-hand boundary of this would be X plus delta X, where delta X is the little distance in between X and X plus delta X. Just a little nudge. Cool. On to the next one. Evaluate the difference of our area function where we put in X plus delta X as our input and then subtract off just the area function. Cool. And think about what this difference has a geometrical meaning in regards to the graph on the last page. If we look at the area function evaluated at X plus delta X, and we subtract off the area function just evaluated at X, I'm going to do part B first. The geometrical meaning is just going to be, this part. The orange, the stuff that I'm starting to shade in orange is, well, actually here, this whole area will be A of X plus delta X, minus A of X. That delta is horrible. But yeah, it's just subtracting the two area functions so you get the difference between the two areas. Yeah, but we're building up this limit, which hopefully looks somewhat familiar. It's the limit definition of the derivative. We're going to be taking the derivative of the area function really soon. But yeah, let's go ahead and calculate this difference. Our area function, let me go ahead and just write that up here, was X squared plus X minus 2. All right. So that'll help us out as we do this problem. We have A of X plus delta X minus A of X. This will equal X plus delta X squared plus X plus delta X, and then minus 2, and then X squared plus X minus 2 is what we're going to subtract off. And yeah, multiplying this out, X squared plus 2X delta X plus delta X squared plus X plus delta X minus 2 minus X squared minus X plus 2. Okay, now a lot of things will be able to cancel here. X squared and minus X squared cancel. Plus X minus X canceled. Minus 2 plus 2 canceled. And all we're left with is 2X delta X plus delta X squared. Oh, actually, there's another delta X over there. Oh, sorry. Yeah, let me go ahead and throw that in here. Delta X plus the delta X squared as what we're left. And, upon further reflection, maybe I should have just labeled this little nudge as H, like we've done in the past, because writing delta X a bunch of times is annoying. Okay, but here we are. X delta X plus a delta X plus a delta X squared. And what we're going to do is evaluate this limit. We're pros at limits now. So really all we have to do is put that in the numerator, 2x delta x plus delta x plus delta x squared. Yikes, that was awful. Delta x, and yeah, we can divide through by delta x and just get 2x plus 1 plus delta x, and yikes, as we take the limit as delta x goes to 0 of this function, we get 2x plus 1. Curious. All right. So if we describe what we just did, taking this limit as delta x goes to 0, we took a derivative. This is the limit definition of the derivative. So we took the derivative of the area function. And we took it with respect to x. Because yeah, we were looking at a little nudge in x and watching what happened as this difference quotient, as delta x went to 0. So yeah, we took the derivative of the area function a of x with respect to x. We got 2x plus 1 as an answer. And what was happening geometrically? Well, if we go back and look at this, if we think about what's happening as delta x approaches 0, you would imagine, this green line getting closer and closer to the blue line, and the orange area here getting smaller and smaller and smaller until, well, basically what happens when we get 2x plus 1 as an answer, really that's just the this function value at that height. Interesting. We're really just getting the height of that, second boundary. 2x plus 1, 2x plus 1. Look at your answer to question number 5, 2x plus 1, and the original function y defined in, question 1, which I should just call this f of t so that we can use f. How are they related? Well, very, very close, right? We started off with f of t equals 2t plus 1, and we end up getting 2x plus 1 at the answer here. Y equals 2t plus 1 versus the derivative of the area function is 2x plus 1. How are they related? They look, very, very similar. They're both linear functions with a slope of 2. They're basically the exact same thing with a change of variable. And then based on what we've explored, describe the relationship between area functions and derivatives that you see. Well, yeah, the derivative of this area function, was actually just the original function evaluated at x. So yeah, if we go up here, we created an area function. We took the limit definition of the area function and got 2x plus 1, and that ended up just being the y value for this, this line when you put in x, 2x plus 1, same thing. So I might summarize it as, the derivative of the area function is the original function. And, that leads us to the fundamental theorem of calculus, part 1. Notice that we have, big f prime of x is equal to f of x. F prime of x is an area function. And we know, since talking about things, when we write the big f of x, that's the antiderivative, or that's an antiderivative. So yeah, the derivative of an antiderivative is the original function. It's describing something very fundamental about the relationship between derivatives and antiderivatives. And in this sense, they undo one another. The derivative is kind of the inverse operation of an integral. So yeah, that's cool. How much time have we spent? I have no idea. I don't know, 15, 20 minutes maybe? That should maybe give you guys enough time to look at this video, about 10 minutes of this video. Will be, 3 blue, 1 brown, explaining the fundamental theorem of calculus with really nice animations rather than my mediocre drawings. And yeah, just to brief you on this, remember in this video, we were looking at the relationship between velocity and position. So the green function here is a velocity function, which is the derivative of position. What we were doing was adding up the area underneath a velocity function to give us the accumulated position. And so, yeah, this video is really cool. Go ahead and watch it, and I'll see you when you get back. Okay, fundamental theorem of calculus, part 1. Yeah, the derivative of an area function is the original function. And yeah, notice that we have to use a variable, like this t. T is sometimes called a dummy variable because it's just, kind of a placeholder at the moment. Yeah, we've got this fundamental relationship between antiderivatives and derivatives. And I think this is a really interesting context because you get to look at a derivative that the geometric interpretation is not the slope of a tangent line. When you're looking at this and you got a little, dt at the bottom, and you're looking at the ratio of, how the positions accumulating here. Yeah, you're not looking at the slope of a tangent line. You're looking at the rate of change of an area function. And the rate of change of an area function ends up being the height of the original function that you're looking at. I don't know. I think that's super cool. Basically our first real example here, we are going to look at some more area functions, but in this case, they are a bit more complicated because their bounds, they don't just have a plain old x like is stated in the fundamental theorem of calculus. Our boundaries are going to be moving at different rates than you might expect. So let's ask the question, what does it look like when we put x squared in a boundary rather than just x? So we're going to look at the function 1 over 2 plus t. We're going to be taking an integral where the first boundary is at some constant a, and the second boundary is at x squared. And then once we've defined that area function, we're going to take the derivative of that area function with respect to x. Let's go to GeoGebra. Whoops. All right, let's move this up. Come on. You can do it, GeoGebra. Refresh. All right. So yeah, this looks great, right? All right, we have a function 1 over 2 plus t. It's our original function. It's the thing that's the integrand inside the integration sign. What I have here are, two different, here actually, let's just look at the blue one for now. This blue one is what will happen if we just take the integral of this function f from a point A. So we're starting off at a equals 0, just so that we start off here. But our second boundary will be at some slidable point x. And I had to name it x var because, yeah, you can't just use x as a slider in GeoGebra. X is a very important letter. But yeah, the idea is we've got an area function again, where we're able to slide x and make, new areas. This part is giving us the value for this specific value of x. Here we've got, x equals 2. Here we've got x equals 3. No big deal. This is giving us the area. Okay, but in the question we were just looking at, come on. In the question we were just looking at, instead of having an x in this upper bound, we have an x squared. And that is going to behave very differently than just a regular old x. So let's include this red one in at the same time and watch how they grow. Okay, so here are area functions. They're sweeping out new area. Notice that at the beginning, for numbers where x is less than 1, x squared is actually less than x. So it's lagging behind for a while. And then once you keep increasing the x value at x equals 1, they're the exact same thing. But, as you go on, and, maybe we stop at pretty close to 2 here. Come on. There we go. Let's stop it at 2. Notice that x squared is already at 4. And so we've actually got a lot more area than the integral that just goes to x as a boundary. And if we went out to 3, x would still be back at 3, but x squared is out at 9. And so you can see how the blue area function and the red area function are pretty different, right? And thinking about the rate of change would be very different. It looks like, initially the red area function would have a slower rate of change, but then after x equals 1, the area function has a greater rate of change, and it's going a lot faster than this, and accumulates a lot more area. For x equals 3, the area function with x squared as a boundary already has 1.7 units of area, where this one's only got 0.92 units of area. So what's going to need to happen when we go back to this is we're actually going to need to use the chain rule, because in here we've embedded a smaller function inside of the area function. Yeah. What our book would have me do is circle this x squared and call it u. You know, in this first one, it would say u is equal to x squared, so that we can tame down, you know, this weird part. Instead of it being squared, we'll just have it be a normal variable u. So we're going to make a substitution here. Also, our book would have me label the entire area function as y, so that we can refer to the entire area function as one variable. So if we were to look at what we have here, if we're treating the entire area function as the variable y, what we have is dy dx. And if we have an embedded function inside the area function, we can use the chain rule to expand this. And so what we can do is say dy du times du dx. If this part doesn't make sense, I'm going to show you another way to do it, or the alternate notation as well. But this is the way that the book would say, do this part, you know, first. Yeah. So if we're looking at dy du, what we would be doing is, you know, just putting u in the place here of x squared. And the area function there, you know, especially, yeah, with respect to x, yeah, what that'll turn out to be is 1/2 plus u. The derivative with respect to x of that part is, yeah, 1/2 plus u. Basically plugging in u where we see t. Yeah, it's like what happens here. This part actually, yeah, no, we're good. And then the next part, the derivative of u with respect to x is 2x. And so what ends up happening is we get 2x over 2 plus x squared as the function that ends up coming out of this. We've performed the chain rule in taking this derivative with respect to x, and we get 2x plus, yeah, or 2x over 2 plus x squared. The alternate notation, you might want to think of this whole thing as you're taking the derivative of the antiderivative with x squared as the argument of your function. So the area function is kind of the antiderivative. This derivative, this prime here, is representing the d over dx. And then x squared is the inside function that's being plugged into the normal fundamental theorem of calculus form. So the right-hand boundary is x squared. What this tells us to do, you know, is write the original function, you know, the thing that's inside here. This part is f of t. I guess maybe, oh, this is getting very crowded. Sorry. But yeah, this part is f of t. So we've got f of x squared, and then times the derivative of x squared, which is 2x. So chain rule again, but yeah, now the chain rule just looks like this. Hmm. Yeah, so I know this looks weird, but we've got an inside function embedded in the area function. When we take this derivative, we need to do it according to the chain rule, which really just means, yeah, plugging in x squared into the function in here, and then multiplying by the derivative of x squared. For the next one, sorry that this is, yeah, taking so long. For the next one, notice that we don't really have the same form of an area function where the bottom or the first left-hand boundary is stationary and the right-hand boundary is the one that moves. In this one, we've got a left-hand boundary that's moving and a right-hand boundary that's stationary. And so what we can do is change this into a better form by using a property of, integrals that we looked at earlier with those definite integrals, and, change the order of the boundaries, but also multiply by a -1. And then, we can do the same kind of thing. I would think of this as we're taking we've got the opposite of the antiderivative, the derivative of the antiderivative, where 3 minus 5x is our input. And if we do that, we're going to need to evaluate f at our input, little f, and multiply that times the derivative of the inside part, which is -5. Okay. So what we end up getting is 5 times the function evaluated at 3 minus 5x, and 5 times e to the 3 minus 5x minus 3 gives us 5e to the minus 5x as an answer there. Chain rule. And then, continue to work things out and just simplify. Okay, last one. We've got 2 movable boundaries on our area function, which is weird. And so the easiest way to do this would be to translate it into 2 integrals, using a property of integrals again. Where, we're going to pick some constant, let's say a. Oh, and actually, hold up. We're going to put a as the top boundary so that we're going to start off at x squared plus 3 and go to some constant a of this function. But then we're going to do a to the end, the right-hand endpoint, 1 plus 5x of cosine t dt. So we're using this stitching property, property number 6 of the definite integral. Come on. We're breaking up the original integral we were given into 2 separate ones so that we can have 2 area functions. So again, this one looks like an area function. This one looks like an area function, but the bounds are backwards because this is the movable left-hand boundary. So what ends up happening is we do the opposite, like we did on this one, and reverse the boundary. But yeah. And since we make this one opposite, normally we bring it to the right-hand side just because it's nicer to write a minus sign rather than I don't know, like a negative sign out in front of this, but yeah. Plus x squared plus 3. Okay, so now we're going from a to x squared plus 3 of cosine t dt plus the derivative of this area function where we're going from a to 1 plus 5x of cosine t dt. I know this is a lot. Let's go ahead and go green again. But yeah, the idea here, if we're treating this one as f prime of x squared plus 3, and this one as f prime of 1 plus 5x, what we can do over here, and this is how we normally handle things, we normally put the first one first and the second, well, we normally flip-flop the order so that we just have a minus sign. And then what we would do the chain rule on both of these. But I guess I want you to notice the pattern here that in order to, this weird thing that had 2 movable boundaries for, creating this area function, in order to get the area here, we are evaluating an area function at the right-hand endpoint, and we're subtracting off the area function up until the left-hand endpoint. That's an important thing. And I'll show you again right here. Let's go ahead and finish this. So what we're doing is putting in cosine of 1 plus 5x times the derivative of the inside, which is 5, minus cosine of x squared plus 3 times the derivative of the inside, which is 2x. So yeah, this is the area, this is the function that you end up getting, derivative of the area function. With chain rule. These are difficult. I was hoping that the notation that I'm using in green will make the most sense to you, but if it's not making sense, we can keep talking about things when I see you next class. All right, moving on to fundamental theorem of calculus part 2, and then we're gonna have to be done with it soon. Fundamental theorem of calculus part 2. This area between, 2 endpoints that are both constant numbers, we're not necessarily making an area function as much as, I guess both of those endpoints are just constant. We're just looking for this static area. what we do is we end up taking the antiderivative of our function f of x and then subtracting f of the antiderivative evaluated at b minus the antiderivative evaluated at a. To me, this is a little bit like learning what happens in the middle by looking at a before and after picture. Yeah, essentially, let me go ahead and zoom out one click. Essentially, what we're doing with this fundamental theorem of calculus part 1 is we're interested in this shaded area in between 1 and 7, let's say. That's A and B. And we're evaluating an area function at B, and then we're evaluating an area function at A. And let's just say, we had defined an area function that, say, started at 0. All right, rainbow. So this entire area, including this spot over here, let's say that is the area function evaluated at 7. And then in order to get the area that we're interested in, we'd have to subtract off the area function evaluated at 1, so that all we're left with is the part that we wanted. So in order to get this definite integral, using the fundamental theorem of calculus part 2, we end up subtracting, evaluated area functions. An area function evaluated at 7 and an area function evaluated at 1. And the difference of those two areas gives us the area that we want. And this, from now on, is going to be how we do integrals. We're going to use this fundamental theorem of calculus throughout all of calculus, all the rest of this class, all of calculus 2, all of calculus 3. This is just going to be the way that we do it. Cool. All right, so let's take a look. Let's actually do a few definite integrals using the fundamental theorem of calculus part 2. The idea is you take an antiderivative. The antiderivative of e to the x is just e to the x because that's its own derivative. And then you evaluate it at 9 and 0. So this notation, you put the antiderivative on the inside of the brackets and you keep your boundaries over here to the right. But eventually what that means is e to the 9th minus e to the 0. The antiderivative evaluated at the top endpoint and the antiderivative evaluated at the left-hand endpoint. And so this is e to the 9th minus 1. And that's a number. And that's the area between 0 and 9 of e to the x, underneath e to the x. Okay. Next one. Antiderivative of 1 over x would be, adding 1 to the exponent. This is the natural log, but we have to make sure that we put that in absolute values because 1 over x has a larger domain than natural log of x. And then we've got the endpoints. And so all this becomes is natural log of 3. And since both of those are positive, I'm just going to write it. Natural log of 3 minus the natural log of 1. And I guess, that's the natural log of 3 over 1, which is just the natural log of 3 as an answer there. So, okay, that's making some sense. But again, it was just that easy. No more limit definition of the integral. We're able to just use 2 antiderivatives, take their difference, and it's great. We get the answer right away. Here we've got x to the 5th. So let's use green. So the antiderivative of x to the 5th, we would add 1 to the exponent, and then divide by that exponent. So it's 1/6 x to the 6th power, evaluated at 1 and -2. So 1/6, 1 to the 6th minus 1/6, -2 to the 6th. Gross. All right. 1/6 times 1, which is just 1/6, minus 1/6 times -2 to the 6th power would be 2 to the 6 would be 64. Okay, so times 64. So this would be -63/6. Cool. You know what? That one's just weird enough that why don't we look at it on GeoGebra? X to the 5th from -2 to 1, and let's make sure this, makes some sense. Don't save. All right. X to the 5th is our function. If we want to get really fancy, we can just go integral of f from -2 to 1, right? -10.5, which is the same thing as -63/6, because I don't reduce my fractions. And yeah, to make this look nicer, let's scale that, yeah, so that we can see. Okay, cool. Yeah, making sense. It does look like we've got more area underneath the x-axis than above the x-axis, so getting a negative signed area for this entire integral makes sense. Cool. I hope you guys are excited that, at the very least, that this process of finding definite integrals is going to go much faster now with the fundamental theorem of calculus part 2. We are almost done with what we need to do today. This one, constructing a function whose derivative is sine of x, which has the function, the value -3 at 0. I feel like we've done a few of these, so we're going to do it really quick. F of x is the one that we don't know. F prime of x is the one that we do know. That one's sine of x. So we take an antiderivative, and we get negative cosine x plus c for some unknown constant. And then if we say f of 0 is equal to -3. So we go -3 is equal to minus cosine of 0 plus c. So -3 equals -1 plus c. And then that's -2 equals c. So f of x should be negative cosine x minus 2. And that should be, at the value -3 at 0. Indeed. Negative cosine x minus 2 does have a y-intercept of -3. Okay, that one, yeah. Again, we're doing antiderivative, so it's not bad, but I feel like we've done that kind of question before. Okay, the next section, we are not going to be able to get through this section, but I do want to introduce it. 5.4 is indefinite integrals and the substitution rule. So on this one, we are going to get more practice. These are just some kind of normal indefinite integrals that we've done in the antiderivative section. But what we're going to work on primarily in this section is the substitution rule, or what's normally known in the biz as U substitution. I just want to give you a heads up that, yeah, we use substitution to undo the chain rule. When we're taking antiderivatives, use substitution is going to help us undo the chain rule. And we're going to get a little bit more systematic about this than what we've done in the past. So yeah, this is something to look forward to. We are going to increase our power in terms of the types of integrals that we're going to be able to evaluate. And yeah, in that next class, we're going to be looking forward to use substitution, using it with definite integrals, using symmetry to evaluate integrals, looking at the area between curves. So, you know, finding areas like this, not just always down to the x-axis. And then also switching our rectangles on their sides and moving up in a dy direction rather than a dx direction, looking at an integral like this. So yeah, that should be fun. Next class. Yeah, this is, I think, we're going to call it a day. And I'll see you next time. Bye.